What if everything we thought we knew about the universe's absolute speed limit was wrong? What if particles could exist that don't just approach the speed of light, but blow right past it, rewriting the rules of reality as they go? For decades, Einstein's theory of relativity has stood as one of the most unshakable pillars of modern physics, insisting that nothing can travel faster than light. But tucked within the equations and imagination of theoretical physicists lies a mind-bending possibility: tachyons. These are not ordinary particles. They are hypothetical entities born from mathematics and mystery, particles said to travel faster than light from the moment they're created, challenging our deepest understanding of time, causality, and the fabric of the cosmos itself. This isn't just science fiction. The concept of tachyons emerges from the same rigorous frameworks that give us black holes, quantum entanglement, and the expansion of the universe. They represent one of the most tantalizing what-if scenarios in all of physics, an idea so radical that it forces us to reconsider not only how the universe works, but what it even means for something to be real. Imagine a particle that experiences time backwards, that gains energy as it slows down, and that could, in theory, allow for communication across time itself. It sounds like fantasy, but it's a possibility that some of the greatest scientific minds have taken seriously for generations. In this video, we're going to embark on a journey into one of the most extraordinary and provocative ideas ever conceived. We'll explore where the concept of tachyons came from, what the mathematics actually says about them, and why, despite decades of searching, they've never been detected. More than that, we'll dive into what the existence of tachyons would mean for humanity, for technology, for philosophy, and for our place in the cosmos. This is more than a tour of theoretical physics. It's an invitation to wonder, to question, and to imagine a universe far stranger and more magnificent than we ever thought possible. So settle in, open your mind, and get ready to explore particles that don't just break the rules, they shatter them. So to understand these bizarre particles, we first need to revisit a cornerstone of modern physics, Einstein's theory of special relativity. This theory gives us the famous equation E equals mc squared, but its real power is in how it defines the relationship between space and time for anything that moves. It established the speed of light in a vacuum as the ultimate cosmic speed limit, a constant that nothing with mass can ever reach, let alone exceed. To accelerate any ordinary object to the speed of light would require an infinite amount of energy, which is, for all practical purposes, impossible. This isn't just a rule, it's woven into the very fabric of reality as we understand it. But here's where things get interesting. While physicists were working with the equations of special relativity, they noticed something peculiar. The math didn't just stop at the speed of light. The equations still produced solutions for particles moving faster than light. These theoretical entities were dubbed tachyons, from the Greek word tachys, meaning swift. They weren't predicted to accelerate past the light barrier. Instead, they were theorized to be born already moving faster than light and to forever remain in that superluminal state. This leads to their most defining and strangest property, imaginary mass. Now, imaginary here doesn't mean make-believe in the everyday sense. It's a precise mathematical term. In the equations, for a particle to have real mass and travel below light speed, certain values must be positive. For a tachyon, that value becomes negative, and the square root of a negative number is what mathematicians call an imaginary number. So, a tachyon's mass is described as imaginary. This unusual mass has a profound and counterintuitive effect on how tachyons behave. For us, in our slow-moving world, when you add energy to an object, it speeds up. A tachyon does the exact opposite. If you try to add energy to a tachyon to push it, it actually slows down. Its speed decreases, bringing it closer to the speed of light from above. Conversely, if a tachyon loses energy, it speeds up, moving even farther away from the light barrier. The ultimate, mind-bending extreme would be a tachyon with zero energy, which would be moving at infinite speed. Think of it like trying to push a car that's in reverse. Pressing the accelerator adding energy wouldn't make it go forward faster, it would just make it reverse more slowly. Taking your foot off the pedal removing energy would make it fly backwards even faster. This is the utterly topsy-turvy world of tachyons, where the fundamental rules of motion are flipped completely on their head. They are not just fast particles, they are entities that operate under a completely different set of physical laws, challenging our most basic intuitions about how the universe is supposed to work. And this bizarre behavior is only the beginning. To truly grasp why tachyons are so revolutionary and so problematic, we have to explore the very framework they threaten to break, Einstein's conception of spacetime. This framework is often visualized using a powerful tool called the light cone. Imagine an event happening right here, right now, a flash of light. The light cone describes all the possible points in spacetime that this flash could ever influence or be influenced by. The forward-pointing cone contains the entire future that the flash could ever reach, traveling at or below light speed. The backward-pointing cone contains all the past events that could have possibly sent a signal to arrive at that exact moment. Everything within this double cone constitutes our universe of cause and effect. For any event to have caused the flash of light, it must lie within the past light cone. And any event that the flash can cause must lie within its future light cone. This structure is the bedrock of causality itself, the unbreakable rule that cause must always come before effect. Now enter the tachyon, a particle that forever travels faster than light would, by its very nature, exist outside of this light cone. From the perspective of our flash of light, a tachyon signal could reach points in spacetime that are considered causally disconnected places that could not possibly be influenced by that event according to the rules of relativity. This is where we encounter the famous and deeply troubling paradoxes. The most famous is the tachyon-antitelephone, a thought experiment where tachyons could be used to send messages into the past. Imagine two scientists, Alice and Bob, moving relative to each other. If Alice sends a tachyon signal to Bob, and Bob immediately sends a tachyonic reply, the rules of special relativity show that from Alice's point of view, the reply could arrive before she even sent her original message. She could receive an answer to a question she hasn't asked yet. This isn't just a quirky puzzle, it creates a logical impossibility that unravels the entire sequence of events we rely on to define reality. If you could send a message to your past self to prevent the invention of the tachyon communicator, how was the message ever sent in the first place? The mathematics of special relativity doesn't explicitly forbid faster than light travel. It simply outlines the chaotic consequences if it were possible. It tells us that if tachyons exist, then for some observers, their effect would literally precede their cause. This challenges the most fundamental principle of physics, not just a single theory. For many physicists, this is the most compelling reason to believe tachyons are a mathematical artifact rather than a physical reality. The universe appears to have a deep-seated aversion to paradoxes that violate causality. The light cone isn't just a suggestion. It feels like a fundamental boundary that the cosmos enforces to maintain a stable, logical order where the past stays in the past and the future remains unknown. So where did this radical idea actually come from? While the mathematical possibility of faster-than-light particles was lurking in Einstein's equations for decades, it took until the late 1960s for the concept to be fully named and explored. The credit for giving tachyons their identity goes to the American physicist Gerald Feinberg. In 1967, he published a landmark paper titled Possibility of Faster-than-Light Particles, and it was here that he formally introduced the term tachyon, derived from the Greek word tachys, which simply means swift. Feinberg wasn't just naming something, he was systematically exploring the properties these particles would have if they were real, including that strange concept of imaginary mass. But the intellectual seeds were planted long before Feinberg put a name to them. Other brilliant minds had already been dancing around the edges of this idea. Decades earlier, the German physicists Arnold Sommerfeld and, independently, the Italian polymath Luigi Fantoppi had encountered similar mathematical solutions in their work. They saw that the equations didn't just stop at light speed and wondered about the implications. However, they often viewed these solutions as problematic artifacts, mathematical curiosities that probably didn't correspond to anything in the real world, or perhaps represented particles that were inherently unobservable. They glimpsed the possibility but largely stepped back from its more revolutionary implications. Feinberg's crucial contribution was to take these mathematical curiosities seriously as potential physical entities. He asked a profound question: if these particles did exist, what would they be like? How would they interact with the world? He proposed that tachyons could be a new class of particles, governed by their own unique quantum field theory, fundamentally different from the ordinary matter we know. He even suggested that if they existed, they might not be able to slow down below the speed of light, which would make them impossible to ever bring to rest and study in a lab, explaining why we had never detected them. This wasn't just a flight of fancy, it was a rigorous physics-based exploration of a once-dismissed idea, elevating it from a mathematical oddity to a legitimate, though highly speculative, subject of scientific inquiry. This historical journey from a dismissed mathematical quirk to a named theoretical concept highlights a beautiful aspect of how science often progresses. It's not always about sudden, dramatic discoveries. Sometimes it's about looking at the same equations everyone else has seen for years but having the courage to ask a different question. Feinberg didn't prove tachyons exist, but he gave physicists a vocabulary and a framework to seriously debate their possibility, pushing the boundaries of what we consider knowable and opening a door to a universe that might be far more wonderfully strange than we ever imagined. To truly appreciate just how alien tachyons are, we need to put them side by side with the particles we know and understand. Our universe is populated by two familiar families, bradyons and luxons. The term bradyon comes from the Greek brades, meaning slow, and it encompasses every particle with mass that we interact with daily: electrons, protons, atoms, you and me. These are all matter particles bound by the cosmic speed limit, forever traveling below the speed of light. Then we have luxons, named for light itself, which are massless particles like photons that must always travel exactly at the speed of light in a vacuum. They can never slow down or speed up, they are forever locked at light speed. Tachyons belong to a hypothetical third category, and their defining characteristic creates a chasm of difference in their behavior. It all comes down to mass. A bradyon, like a proton, has what we call a real positive rest mass. This mass is a measure of its inertia, its resistance to acceleration. Because of this mass, it requires more and more energy to push it closer to light speed, with that energy requirement soaring toward infinity. A luxon, like a photon, has zero rest mass. This is why it can travel at light speed without requiring infinite energy. It has no mass to accelerate. It simply exists in a perpetual state of motion at the universe's ultimate velocity. A tachyon, by contrast, possesses an imaginary mass. This isn't a judgment on its existence, but a precise mathematical description. The equations show that its mass squared is a negative number, and the square root of a negative number is imaginary. This single, profound difference flips the entire rulebook of particle behavior on its head. For a bradyon, adding energy increases its speed. For a tachyon, adding energy decreases its speed, bringing it closer to the unattainable barrier of light speed from above. To slow a tachyon down, you have to pour energy into it. This leads to an almost surreal conclusion. A tachyon with infinite energy would be traveling at the speed of light, while a tachyon with zero energy would be moving at infinite speed. Their relationship with time further separates them. Bradyons and luxons operate within our familiar flow of time, where cause precedes effect. Tachyons, by traveling outside the light cone, would experience space-time in a way that could make effect precede cause from certain perspectives, leading to those universe-breaking paradoxes. While a photon is the ultimate messenger, instantly connecting events across space at light speed, a tachyon would be a potential messenger from the future, a signal that could loop back on the timeline itself. This comparison isn't just an academic exercise. It shows us that the stable, causal universe we inhabit is fundamentally built upon the properties of bradyons and luxons. The introduction of tachyons wouldn't just add a new particle. It would require a complete and radical rewriting of the laws of physics as we know them, challenging the very notions of reality that we take for granted. This concept of imaginary mass is perhaps the most misunderstood aspect of tachyons, and it's crucial we unpack what it truly means. We must first divorce the word imaginary from its everyday meaning of being make-believe or fictional. In mathematics, an imaginary number is a perfectly valid concept, defined as the square root of a negative one, represented by the symbol I. So, a number like 2i simply means 2 times the square root of -1. This isn't a sign of something unreal. It's a different kind of real, a tool that allows us to describe phenomena that can't be captured by our standard number line, and it's used extensively in fields like electrical engineering and quantum mechanics. For a particle with real mass, like an electron, its mass is a positive value. When we plug this into Einstein's famous equation, everything works seamlessly. But the equations of special relativity are more like a map of all possible motion, not just the motion we commonly experience. If you mathematically describe a particle traveling faster than light, the term for its mass squared becomes a negative number. To find the mass itself, you must take the square root of that negative number, which is how you arrive at an imaginary value. So, a tachyon wouldn't have a mass you could place on a scale. Its mass would be a value like I times some number, say 5i kilograms. This isn't a statement that its mass doesn't exist, but rather that it exists as a different type of quantity, one that operates outside our conventional understanding of matter. This mathematical oddity translates into a physical reality that is utterly inverted. For any ordinary object, its rest mass is the mass it has when it's not moving. A tachyon, however, can never be at rest. It is forever condemned to travel faster than light, and its rest mass is a conceptual phantom, a value we calculate by extrapolation, not something we could ever actually measure because bringing it to rest would require infinite energy. This imaginary mass is the mathematical key that unlocks its bizarre behavioral lock. It explains why adding energy to a tachyon slows it down. You are essentially feeding energy into a system governed by these inverted rules, pushing it closer to the unreachable barrier of light speed from the faster-than-light side. The more you push, the more it resists by slowing its incredible pace. The strangeness doesn't stop there. This imaginary mass also has profound implications for how tachyons would interact with the world, particularly through gravity. According to general relativity, gravity is the curvature of spacetime caused by mass and energy. But what kind of gravity would a particle with imaginary mass produce? Some theoretical work suggests that tachyons might have negative gravitational mass, meaning they would repel rather than attract ordinary matter. Picture a universe where some particles are gravitationally attracted to each other, while these phantom particles are gravitationally repelled, forever pushing away from the structured cosmos we know. This isn't just a minor tweak to physics. It suggests a fundamental duality in the fabric of reality itself, a hidden anti-gravity realm of particles that could only ever interact with our world in the most fleeting and paradoxical ways. The imaginary mass is not a flaw in the theory. It is the precise mathematical signature of a reality turned inside out. The most profound and unsettling consequence of tachyons isn't their speed or their strange mass, it's their potential to shatter the very sequence of events that gives our universe its logical structure. This threat to causality is the single biggest reason many physicists dismiss tachyons as mathematical phantoms rather than physical realities. To understand why, we need to examine the most famous of these temporal paradoxes, the grandfather paradox. Imagine you could use a tachyon-based device to send a message back in time to your own grandfather when he was a young man. The message instructs him to avoid meeting your grandmother. If he heeds the warning, the meeting never happens, your parent is never born, and consequently, you are never born. But if you were never born, who sent the message back in time to alter events in the first place? The entire scenario creates an unsolvable logical loop where the effect preventing your own birth erases the cause, you sending the message. It's a contradiction that cannot exist in a consistent logical universe. This paradox emerges directly from the geometry of spacetime as described by special relativity. The theory allows for different observers to disagree on the order of events if those events are separated by a space-like interval, meaning no light signal could connect them. For any particle or signal traveling slower than light, all observers will always agree that the cause happened before the effect, but a tachyon moving faster than light lives in this space-like realm. From the perspective of one observer, a tachyon signal might be sent from point A and received at point B in the correct order. However, for another observer moving at a high relative velocity, the math of relativity shows that the very same tachyon signal would appear to be received at point B before it was ever sent from point A. The effect would literally precede the cause in their frame of reference. This isn't a quirk of perception. It's a fundamental property of how spacetime is woven together, and the introduction of a faster-than-light signal tears at that fabric. This leads to a more precise, physics-based thought experiment than the grandfather paradox, known as the tachyon-antitelephone. Picture two scientists, Alice and Bob, stationed on different planets light-years apart. They are both equipped with a device that can send and receive messages via tachyons. Alice decides to send a message to Bob asking a simple question like, "What is the capital of France?" Because the tachyon travels faster than light, her message arrives at Bob's station almost instantly from her perspective. Bob immediately receives the message, looks up the answer, and sends a tachyonic reply, Paris. Now, due to their relative motion and the bizarre rules of spacetime for tachyons, it is mathematically possible for Alice to receive Bob's reply, Paris, before she even decides to send her original question. She gets the answer before the question is asked. This creates a closed loop of information with no origin, a reality where knowledge simply pops into existence from nowhere, completely violating the principle that information cannot be created or destroyed. The implications of this extend far beyond clever puzzles. Our entire understanding of physics, from the motion of planets to the collisions of subatomic particles, is built on the unshakable foundation of causality. Every equation, every prediction, and every experiment assumes that causes lead to effects, not the other way around. If this principle fails, the entire predictive power of science collapses. We could no longer run experiments with any confidence because the outcome of an experiment could theoretically influence its own setup in the past. The universe would become an unpredictable, chaotic place where the laws of physics as we know them cease to have any meaning. For most scientists, the robust consistency of the universe we observe is the strongest evidence that such causality violations are forbidden by a deeper, yet to be understood law of nature. Tachyons represent a fascinating what-if, but their potential to create these logical impossibilities suggests they are likely a door the universe has firmly locked shut. To see if tachyons could ever be more than a mathematical curiosity, we have to move beyond the clean lines of special relativity and venture into the more complex and probabilistic world of quantum field theory. This is the framework that combines quantum mechanics with special relativity to describe not just particles, but the underlying fields that permeate all of spacetime. Think of the universe not as a collection of tiny balls, but as an ocean of invisible fields, an electron field, a quark field, a Higgs field, and what we perceive as particles are simply localized vibrations in these fields. It is within this sophisticated context that the concept of a tachyon takes on a fascinating and surprisingly practical new meaning, one that is less about breaking light speed and more about revealing instability. In quantum field theory, each type of particle corresponds to a specific quantum field. The properties of that particle, most importantly its mass, are determined by the shape of the potential energy of its field. For a stable field like the electron field, this potential is like a bowl. The lowest energy state, the vacuum, is at the bottom of the bowl. A vibration, an electron, has a positive mass squared and sits happily in this stable valley. Now imagine a field whose potential is shaped not like a bowl, but like an upside-down bowl, a hill. The point at the very top of the hill seems like a possible vacuum state, but it's inherently unstable. The slightest nudge would send it rolling down. In the language of quantum field theory, a vibration in a field with such an inverted potential would have a negative mass squared the mathematical signature of a tachyon. This is where the idea of tachyon-condensation comes into play. It's a process where a system that appears to be tachyonic and thus unstable doesn't actually produce faster than light particles. Instead, it rapidly transforms or condenses into a new, stable configuration. The Higgs mechanism, which gives other particles their mass, is the most famous and successful example of this. Before the Higgs field acquires its value, its potential has that unstable, hill-like shape. The calculations suggest it would have a negative mass squared, making it look tachyonic. But this doesn't mean the Higgs boson is zipping around faster than light. It means the vacuum state we currently live in is not the true, stable vacuum of that field. The Higgs field quickly rolled down the hill and settled into a stable valley, a process we call electroweak symmetry breaking. What was a tachyonic instability became the mechanism that gave mass to the universe. So, in the modern interpretation, a tachyon in quantum field theory is rarely seen as a literal particle. Instead, it's a red flag in the mathematics, a warning sign that the system you're describing is in an unstable state and is poised to undergo a dramatic phase transition to find its true, stable ground state. It's the physics equivalent of balancing a pencil perfectly on its point. The equations might allow for that solution, but in reality, the pencil will always fall over. The tachyon isn't the pencil moving at impossible speeds. It's the unmistakable signal that the pencil is about to fall. This perspective dramatically reframes the entire tachyon conversation. While the thought experiment of a faster-than-light particle is thrilling, its appearance in our most advanced theories is often a call to look deeper for a more profound stability. It shows us that the universe has a powerful tendency to avoid paradox and instability, not through prohibition but through transformation. The mathematics doesn't lie, it just sometimes points to a reality that is transient, a fleeting state on the way to something more solid and structured. The ghost of the tachyon, therefore, isn't a specter haunting physics with paradoxes, but a guide revealing the path to a deeper understanding of how our universe found its stable and massive form. Yet the story of tachyons doesn't end with quantum field theory's elegant resolution of instability. It takes an even more fascinating turn when we venture into one of the most ambitious frameworks in all of physics, string theory. Here, the tachyon reappears not as a bug in the equations, but as a central feature pointing toward profound and potentially universe-altering possibilities. String theory proposes that the fundamental building blocks of reality are not point-like particles but tiny, vibrating strings. The different vibrational patterns of these strings correspond to the different particles we observe, from photons to electrons. And within the spectrum of vibrations for open strings, strings within points that are not looped, the mathematics once again reveals a state with a negative mass squared. This is the string-theoretic tachyon. In this context, the tachyon is interpreted as a clear signal of instability, but on a cosmic scale. It suggests that the vacuum state of spacetime that our universe currently resides in might not be the true, stable ground state. Think of it as our entire universe precariously perched on the top of a vast energy hill. It's stable enough for now, but it's not its forever home. The presence of this tachyonic mode in the string spectrum indicates that this configuration is metastable, and the tachyon field itself holds the potential to trigger a cataclysmic transition to a lower, truer vacuum. This process is known as tachyon-condensation, and it is the string theory equivalent of the Higgs mechanism, but with consequences that are literally universal. The condensation of this tachyon field is theorized to represent the decay of the unstable D-brane, a multidimensional object to which open strings are attached. As the tachyon condenses, the D-brane effectively dissolves, and the open strings that defined our physical laws and particles simply vanish. This isn't just the end of a star or a galaxy. It's a fundamental rewriting of the laws of physics themselves in a region of space. It would create a bubble of a new, true vacuum that would expand outward at the speed of light, its wall erasing everything in its path and replacing it with a new reality governed by completely different physical constants. From our perspective, it would be the absolute end of everything. One moment the universe exists, and the next it has been seamlessly overwritten by something else. However, string theory also offers a more hopeful, or at least less destructive, interpretation. Some theories suggest that this tachyon-driven decay might not lead to nothingness, but to a different, more stable universe. The condensation could be the mechanism that transforms one type of brain, and thus one set of physical laws, into another. It could be the physics behind a cosmic reboot, a transition from one vacuum state to another within the vast landscape of possible universes predicted by string theory. In this view, our universe's apparent stability is a temporary phase, and the tachyonic instability is a hidden reminder that we are part of a much larger, dynamic multiverse, constantly in flux, with the seeds of our own transformation woven into the very fabric of the strings that construct reality. The tachyon becomes not just a herald of doom, but a potential key to understanding the deepest architecture of existence. Given the profound theoretical implications, it's only natural that physicists would want to search for tangible evidence. So, how does one actually hunt for a particle that, by its very definition, might be fundamentally undetectable? The search for tachyons has been a story of ingenious experimental creativity, facing down one of the most challenging quests in modern physics. Unlike the hunt for the Higgs boson or gravitational waves, researchers aren't looking for a clear signal predicted by a settled theory. They are sifting through noise for the ghost of a mathematical possibility, an anomaly that could rewrite the rules. Some of the most direct searches have taken place in the controlled chaos of particle accelerators. If tachyons are real and can interact with ordinary matter, one might expect them to be created in the high-energy collisions inside machines like the Large Hadron Collider. Physicists have looked for their signature in the aftermath of these tiny Big Bangs. One proposed method involves searching for Cherenkov radiation in a vacuum. Normal Cherenkov radiation is the beautiful blue glow produced when a charged particle, like an electron, travels through a medium like water faster than light can travel in that medium. It's a light boom analogous to a sonic boom. A charged tachyon, however, would theoretically produce Cherenkov radiation even in a perfect vacuum because it would always be traveling faster than the vacuum speed of light. Detecting such a glow in an empty chamber would be a stunning, almost unmistakable signature of a superluminal particle. Despite meticulous searches, no such vacuum Cherenkov radiation has ever been observed. Another approach has been to look for the energy fingerprints of tachyon decay. If a tachyon were created in a collision and then decayed into slower-than-light particles, the unique geometry of its existence would impose specific and unusual conditions on the energies and angles of those daughter particles. Experimenters have analyzed countless collision events, searching for these statistical anomalies in the data that might betray the brief existence of a tachyon parent. So far, the data from colliders around the world has shown no convincing evidence for such events. Every result has come back consistent with the standard model of particle physics, which has no place for tachyons. Beyond Chinese letter confines of particle accelerators, scientists have also turned to the cosmos as a natural laboratory. The universe is constantly bombarding Earth with high-energy particles from deep space known as cosmic rays. Some of these particles carry energies far greater than anything we can produce in our accelerators. If tachyons exist, they might be created in violent astrophysical events like supernova, gamma-ray bursts, or in the energetic environments around black holes. Experiments designed to detect cosmic rays, such as extensive air shower arrays that measure the cascades of particles created when a cosmic ray strikes the atmosphere, have also been used to look for tachyons. The idea is that a tachyon, due to its inverted energy-speed relationship, would behave very differently as it passed through the atmosphere compared to a normal particle. It might lose energy and speed up, creating a distinctive and unexpected shower profile. Again, despite decades of observation, no clear, reproducible evidence has emerged from these cosmic watchposts. The consistent negative results from all these experiments might seem like a closed case, but the story is more nuanced, and this is why the tachyon hypothesis persists in the imagination of physicists. A null result doesn't always mean something doesn't exist. It can also mean we're looking for it in the wrong way, or that its nature makes it invisible to our current methods. Several compelling reasons explain why we haven't ruled out tachyons entirely. First is the possibility that tachyons simply do not interact with ordinary matter via any of the known fundamental forces, or they interact so weakly that our detectors are blind to them. They could be their own separate cosmic sector, zipping through our labs and our bodies at superluminal speeds without leaving a trace, forever isolated from the world of light and matter we inhabit. A second, more subtle reason is based on their defining property. If adding energy to a tachyon slows it down, then the highest energy tachyons would be the ones moving closest to the speed of light. The lower energy ones would be impossibly fast. Our most sensitive detectors are tuned to find high-energy phenomena, but the very tachyons we might most easily create and detect in our high-energy colliders would be the ones behaving almost like light-speed particles, making them incredibly difficult to distinguish from ordinary radiation. The most unmistakably tachyon-like particles, the low-energy, infinite-speed phantoms, would be nearly impossible to generate or catch. We may be looking for a faint whisper in a frequency range where the particle only knows how to shout. The failure to find them isn't a definitive proof of their absence. It's a testament to the profound challenge of detecting a particle that operates by a completely inverted set of physical laws. The search continues, not with the expectation of immediate success, but with the understanding that to not look would be to ignore one of the most tantalizing possibilities the universe's equations have ever offered. The most precise and chilling demonstration of this threat is a thought experiment known as the tachyon-antitelephone. This isn't a physical machine, but a logical device designed to expose the fatal flaws in faster-than-light communication. To see how it works, let's set up a scenario with two characters, Alice and Bob. Imagine they are astronauts living in a future where humanity has colonized distant stars. Alice is stationed on a research outpost orbiting a planet near Alpha Centauri, while Bob is on a similar outpost circling a world near Sirius. These stars are separated by several light years. Both Alice and Bob possess a miraculous device, a communicator that can send and receive signals using tachyons. Now, their two outposts are not stationary relative to each other. they are moving apart at a significant fraction of the speed of light. This relative motion is the key ingredient that makes the paradox possible, because in Einstein's relativity, observers in high-speed motion can disagree on whether two events are simultaneous. One day, Alice decides to test her new device. At exactly 12 o'clock noon by her station's clock, she composes a simple message to Bob. "What is the weather like on your world today?" And sends it via tachyon, because her tachyon transmitter is tuned to send particles moving vastly faster than light. From her perspective, the message arrives at Bob's station almost instantly. Bob receives the message just moments after she sends it. He looks out his viewport, sees it's a lovely day, and immediately sends a tachyonic reply. The weather is clear and sunny. Here is where the laws of physics twist reality into a logical knot. Due to their high relative velocity, the rules of special relativity dictate that from Alice's frame of reference, the events are not ordered as she intuitively expects. The mathematics shows that the tachyonic reply Bob sends can actually arrive at Alice's station before she ever decided to send her original question. From the perspective of her own clock, she might receive the message, "The weather is clear and sunny," at 11:59 a.m., a full minute before she even sat down to type, "What is the weather like on your world today?" She receives an answer to a question she hasn't asked yet. This is more than just a curiosity. It creates a closed loop of information with no origin. Where did the information about the weather come from? It seemingly popped into existence from nowhere. Alice could then, at noon, decide not to send the message at all, creating the same grandfather paradox on a smaller scale. If she doesn't send the message, then Bob never receives a question and never sends a reply. But if he never sends a reply, then she never received an answer that convinced her not to send the message in the first place. The chain of cause and effect is completely shattered, leaving a logical inconsistency that cannot be resolved. This paradox isn't a limitation of our technology, it's a fundamental property of spacetime itself. The tachyon-antitelephone demonstrates that any form of faster-than-light communication, not just tachyons, would inevitably lead to these causality violations. The universe's construction seems to have a deeply embedded rule that prevents effect from preceding cause for all observers. This thought experiment strongly suggests that if tachyons did exist and could interact with our matter to transmit information, the very foundations of reality would become unstable. The consistent laws we rely on to understand everything from a falling apple to the expansion of the cosmos would crumble into a chaotic mess where prediction becomes impossible. It is this profound argument from causality, more than any failed experiment, that leads most physicists to believe tachyons as information-carrying particles are an impossibility. The universe appears to protect its own logical consistency by forbidding any signal from outrunning a beam of light. This brings us to one of the most thrilling and contentious ideas in theoretical physics. Could tachyons be the key to time travel? The connection seems almost inevitable. If a tachyon can deliver a message that arrives before it's sent, then it hasn't just broken the speed limit, it has effectively sent information into the past. This isn't mere speculation, it's a direct consequence of the mathematics we've been exploring. But before we envision hopping into a DeLorean powered by tachyons, we have to confront the brutal logical paradoxes this creates. The grandfather paradox and the tachyonic-antitelephone aren't just fun thought experiments. They are glaring warning signs that our current understanding of physics cannot accommodate such a possibility without collapsing into nonsense. In response to this profound problem, some physicists have proposed a radical way out, the concept of consistent histories. This approach, rooted in quantum mechanics, asks a deceptively simple question. What if the universe simply forbids paradoxes from happening? Instead of causing a logical inconsistency, any attempt to change the past would result in a sequence of events that is entirely self-consistent, even if it seems bizarre from our linear perspective. Imagine you receive a tachyon message from the future with the blueprints to build a tachyon communicator. You then build it and send that very same message back to your past self. The information has no origin. It exists in a closed, stable loop. You didn't create the blueprints, you just always had them. The universe, in this view, would only allow histories that are consistent from start to finish, seamlessly weaving the effects of time travel into the fabric of reality so that everything remains logically sound. This idea pushes us into the realm of scenarios where the past is not a fixed point to be altered but a part of a single, unchangeable timeline. Your attempt to go back and stop an event would be the very reason that event happened in the first place. Your actions in the past were always a part of history. While this resolves the logical paradox, it introduces a deep and unsettling sense of determinism, a universe where free will might be an illusion and every event is preordained in a complex, self-reinforcing loop. For many, this price is too high to pay, feeling more like a philosophical surrender than a scientific solution. It suggests that time travel might be possible, but only if we are utterly powerless to change anything that has already happened. Another perspective emerges from the many worlds interpretation of quantum mechanics. This theory proposes that with every quantum decision, the universe splits into multiple branches, creating a vast and ever-growing multiverse of parallel realities. In this model, a tachyon might not travel into its own past at all. Instead, it could be hypothesized to jump between branching timelines. If you tried to send a message back to prevent a disaster, you wouldn't be altering your own history. You would be contacting a parallel universe, a different branch of reality, and warning that version of you. Your original timeline remains unchanged with the disaster still happening, but another universe gets a different outcome. This avoids the paradox entirely because the effect doesn't loop back to its own cause. It influences a separate, independent reality. Each of these models, consistent histories and many worlds, offers a clever mathematical workaround to the causality problem, but they come with enormous metaphysical baggage. They require us to accept that the universe is either predetermined in every detail or that we are part of an infinite sea of alternate realities. More critically, they all hinge on a giant, if tachyons exist, and if they can be controlled to carry information, and if they interact with our world in a way that allows for such precise engineering. The overwhelming consensus in physics is that these are too many unstable assumptions stacked upon one another. The universe's steadfast refusal to show us any evidence of tachyons or any violation of causality suggests a simpler answer, that the laws of physics as we know them are structured to prevent time travel altogether, preserving a stable, logical universe where cause always and definitively precedes effect. The dream of tachyons as a time machine remains one of the most captivating ideas in science, but it appears to be a door that the universe has not only locked but thrown away the key. Faced with these universe-breaking paradoxes, some of the most brilliant minds in physics have proposed a fascinating and elegant solution. The universe might possess a kind of built-in self-defense mechanism. This idea is often discussed in the context of the cosmic censorship hypothesis, a concept originally proposed by the renowned physicist Roger Penrose. While Penrose initially applied this to the singularities within black holes, suggesting that nature abhors a naked singularity and always shrouds it behind an event horizon to protect causality, the principle can be extended much further. It suggests that the laws of physics themselves may actively prevent us from ever observing or interacting with anything that could lead to a logical paradox, effectively acting as a cosmic censor. In the case of tachyons, this censorship wouldn't require a conscious entity making decisions. It could be an inherent property of how reality is constructed. One compelling way this could work is through a total lack of interaction. Tachyons might exist in a parallel sector of reality, a shadow universe that operates by its own inverted rules, but they are completely incapable of exchanging energy or information with our world. They could be streaming through us right now, but if they don't interact via the electromagnetic force, we couldn't see them. If they don't interact via the strong or weak nuclear forces, they wouldn't affect matter. And if their imaginary mass produces repulsive gravity, as some theories suggest, they might even be pushing away from the planets and stars made of our ordinary matter, ensuring a permanent and total separation. They would be forever phantoms, real in a mathematical sense but completely undetectable and irrelevant to our causal reality. Another, more subtle form of censorship could be through random noise. Imagine if a tachyon signal aimed at creating a paradox was somehow scrambled during its journey. Any meaningful information it carries, like the message, "Don't build this machine," would be lost, degraded into random, useless static by the time it arrives. The signal would be present, but its content would be censored into incoherence. The universe would allow the effect to precede the cause, but the effect would be so garbled that it couldn't actually be used to change the past in a logical way. It would be like receiving a radio transmission from the future that consists of nothing but white noise. The phenomenon occurs, but the paradoxical information is erased, preserving the consistent flow of history. This idea of cosmic censorship offers a powerful and philosophically satisfying resolution to the tachyon dilemma. It suggests that the equations of physics might allow for a wider range of possibilities than what we actually observe, but that nature itself draws a boundary around the permissible. The truly paradoxical elements are quarantined, hidden behind a veil we cannot pierce. This isn't a failure of our science, it's a profound feature of the universe, a hidden rule that maintains stability and logic. It means that tantalizing solutions for faster-than-light particles in our textbooks might be real, but their most dangerous implications are neutered by a deeper law we have yet to fully understand, a law that places causality itself as the highest and most protected principle in all of existence. While the search for real tachyons continues in laboratories and cosmic ray data, they have already found a permanent home in the realm of science fiction, where their theoretical weirdness makes them the perfect plot device. Perhaps the most famous pop culture appearance is in the expansive universe of Star Trek. Here, tachyons are treated not as elusive phantoms but as a detectable, almost mundane tool. Starships like the Enterprise use tachyon detection grids to scan for cloaked Romulan warbirds, their sensors tuned to the unique signature of these faster-than-light particles. This series often portrays tachyons as a kind of energetic emission that can be generated, directed, and blocked, much like a radio wave. In one particularly clever story, a tachyon pulse is used to create a temporal causality loop, trapping the crew in a repeating day, a direct nod to the real-world grandfather paradox that tachyons inspire, beautifully simplified for a television audience. Beyond the final frontier, tachyons have become a versatile shorthand for advanced technology and cosmic mystery in countless other stories. In the iconic cartoon The Real Ghostbusters, the team upgrades their proton packs with tachyon accelerators to fight a powerful entity, lending a veneer of scientific credibility to their paranormal pursuits. The video game Civilization features a tachyon project as a futuristic energy source, positioning it as the ultimate achievement of a technologically mature society. These uses strip away the complex physics and unsettling paradoxes, instead leveraging the name tachyon to instantly communicate a sense of cutting-edge, almost magical science that operates just beyond our current understanding. The concept truly shines in narratives centered on time travel and communication, themes for which tachyons are a natural fit. Many novels and films use them as the proposed mechanism for sending messages across time, directly borrowing from the tachyon-antitelephone thought experiment. A character might discover a device that uses a tachyon beam to contact the past, only to inadvertently create the very situation they were trying to prevent. This allows writers to explore classic time travel tropes, paradoxes, fate, and the illusion of free will while grounding their story in a concept that has at least some basis in real theoretical physics, making the impossible feel tantalizingly plausible. This cultural adoption reveals something fascinating about our relationship with complex science. Most viewers and readers will never grapple with the equations of special relativity or the nuances of imaginary mass, but through these stories they become familiar with the idea. The word tachyon enters the lexicon not as a frightening mathematical abstraction, but as a symbol of human ingenuity and wonder. It represents the hope that the universe's greatest mysteries are not impenetrable barriers but puzzles waiting to be solved, and that the very laws that seem to constrain us might one day be harnessed to achieve the impossible. Science fiction doesn't need to be perfectly accurate. It needs to be inspiring, and in that mission, the tachyon has become one of its most reliable and evocative stars. Yet despite the paradoxes that make most physicists deeply skeptical, it's an irresistible exercise to wonder what we could achieve if these particles were real and we could somehow tame them. The potential applications would be nothing short of revolutionary, transforming every facet of our civilization from the ground up. The most immediate and profound application would be in the realm of communication. Imagine a network of transceivers capable of sending messages using tachyons. Unlike our current methods reliant on radio waves or lasers, which are limited to the speed of light, a tachyon signal would be instantaneous from our perspective. A message sent from a colony on a planet orbiting Proxima Centauri, over 4 light-years away, would arrive on Earth not 4 years later, but in that very same moment. We could have real-time conversations with explorers in other star systems, creating a truly connected interstellar community where distance is no longer a barrier to conversation. This wouldn't just be a faster internet, it would be a fundamental rewiring of human interaction on a galactic scale, turning the vast emptiness of space into a familiar neighborhood. This breakthrough in communication would inevitably lead to a revolution in energy. Remember the tachyon's bizarre relationship with energy. To slow it down, you have to add energy to it. This implies that a slowed-down tachyon would have more energy than a faster one. In theory, one could design a device that captures high-speed tachyons and forces them to slow down by transferring their kinetic energy into a usable form. This would essentially be a generator that draws energy from the boundless kinetic reservoir of particles moving at superluminal speeds. It would be like building a dam, but instead of holding back water, it would be harvesting the momentum of particles that are fundamentally unbound by our universe's speed limit. This could provide a virtually limitless and clean power source, solving humanity's energy crisis forever by tapping into a dimension of physics we currently cannot access. The most mind-bending applications, however, might emerge in the field of computing. A tachyon-based computer would not operate under the same sequential, cause-and-effect logic that governs our current digital systems. Because tachyons can challenge the linear flow of time, such a computer could potentially perform calculations where the result is available before the calculation is even initiated. This isn't just about speed, it's about a completely different computational paradigm. Problems that are currently intractable for classical computers, like certain types of complex simulations or optimization puzzles, might be solved instantaneously by a system that can effectively process information backwards and forwards in time. It would be less of a calculator and more of an oracle, providing answers that seem to emerge from the very fabric of a non-linear timescape, leveraging the paradoxical nature of tachyons to achieve a form of processing that we can scarcely imagine today. Given these monumental hurdles, how would we even begin to look for something that might be fundamentally designed to evade our senses? The challenge of detecting tachyons would be the ultimate scientific puzzle, requiring us to build traps for phantoms and design telescopes for the logically impossible. One of the most promising theoretical avenues involves searching not for the tachyons themselves, but for the unique wake they would leave behind. Just as a supersonic jet creates a sonic boom, A charged particle moving faster than light through a medium produces a shockwave of radiation known as Cherenkov radiation, that characteristic blue glow seen in nuclear reactor pools. A charged tachyon, however, would be moving faster than light even in a perfect vacuum, the one place where ordinary particles can't achieve that feat. This means a tachyon should theoretically produce Cherenkov radiation in complete emptiness, a phenomenon known as vacuum-Cherenkov radiation. Building an exquisitely sensitive detector designed to look for this impossible glow in a deeply shielded vacuum chamber could be our first glimpse of a superluminal world. It would be a signature that screams its origin, a light boom in the silent void where no boom should ever be. Beyond the controlled environment of a lab, we could turn our gaze to the cosmos, using the universe itself as a giant particle accelerator. Astrophysical cataclysms like supernova explosions, gamma-ray bursts, or the violent environments around rotating neutron stars generate energies that dwarf anything we can produce on Earth. These events could be natural tachyon factories. If tachyons are created there and can interact with ordinary matter, even briefly, they would decay into slower than light particles in a very distinctive way. Their unique energy relationships would impose unusual and asymmetric patterns on the resulting particle showers. Giant cosmic ray observatories like the Pierre-Auger Observatory already map the vast cascades of particles created when high-energy protons from deep space hit our atmosphere. Physicists could meticulously analyze these events, sifting through petabytes of data for the statistical fingerprint of a tachyon-initiated decay, an anomaly that simply doesn't fit the standard model's playbook. Perhaps the most mind-bending approach would be to look for evidence of their most infamous property, causality violation. This wouldn't involve catching a tachyon in a jar, but rather identifying an event in the heavens so bizarre that it defies any other explanation. Imagine two distant galaxies where a supernova explosion in one galaxy appears to trigger an identical supernova in the other, but the trigger event is observed to happen after the event it supposedly caused, even when accounting for the finite speed of light. Or consider a deep space phenomenon where information about a stellar eruption seems to arrive at a detector before the light from the eruption itself. These wouldn't be subtle signals, they would be monumental violations of the natural order, cosmic glitches that would force us to completely reconsider our understanding of time. Astronomers would search for these paradoxical correlations across the sky, looking for any event where the effect demonstrably and reliably precedes its cause on an interstellar scale, the ultimate smoking gun for a universe interlaced with faster-than-light threads. Each of these methods pushes the boundaries of our current technology and imagination, a testament to the profound challenge of hunting for a particle that operates by a different set of rules. The failure to find them so far isn't necessarily a dead end. It might simply mean we haven't yet learned how to see the evidence that's right in front of us, or that the universe's cosmic censorship is more effective than we ever dreamed. This brings us to one of the most profound reinterpretations of the tachyon concept, a theory that moves beyond the idea of a particle and into the realm of cosmic metamorphosis. While the image of a lone tachyon zipping through space is compelling, modern theoretical physics often views them not as independent entities, but as signals of a profound instability within a system, a state yearning to transform into something stable. This process is known as tachyon-condensation, and it's a concept that connects the fate of tachyons to the very origin of mass in our universe and its potential ultimate end. To visualize this, let's step away from particle physics for a moment and think about the states of matter we know. Consider water. When liquid water is supercooled below 0 degrees Celsius, it exists in a precarious, unstable state. The slightest disturbance, a speck of dust or a gentle tap, causes it to rapidly crystallize, transforming into stable, solid ice. The supercooled water is unstable, the ice is stable. Tachyon condensation is the physics equivalent of this rapid freezing. but on a scale that governs the fundamental fields that make up reality itself. In quantum field theory, the state of lowest energy for a field is called its vacuum. We often think of a vacuum as pure emptiness, but in physics, it's a seething, vibrant background where fields reside at their most relaxed, stable configuration. Now imagine a field that, instead of sitting at the bottom of a valley, is perfectly balanced on the tip of a very sharp hill. This is an unstable vacuum. The mathematics describing vibrations in such a field show they have a negative mass squared the hallmark of a tachyon. So, the presence of a tachyon in the theory is a giant, flashing warning sign that says, this vacuum is unstable. This entire configuration is poised to collapse. This isn't just abstract math, it's the leading theory for how our universe acquired its fundamental properties. The most famous example is the Higgs mechanism. Before the Higgs field acquired the value it has today, its potential energy landscape was shaped like that unstable hill. Calculations showed it was in a tachyonic state, but this didn't mean the early universe was full of faster-than-light Higgs particles. It meant the entire Higgs field was unstable and desperately wanted to change. In a flash, it underwent a phase transition, rolling down the hill and settling into a stable valley. As it did, it broke the symmetry of the electroweak force and, crucially, gave mass to elementary particles like electrons and quarks. The tachyon here wasn't a thing to be detected. It was the symptom of an instability that, once resolved, gave the universe the structure we recognize today. The ghost of the tachyon was the catalyst for the existence of mass itself. This concept takes on an even more dramatic and almost apocalyptic dimension when applied to the vacuum of spacetime as a whole. Some theories, particularly within string theory, suggest that the vacuum our universe currently resides in might not be the true, absolute ground state. It could be a false vacuum, a local stability that is ultimately metastable, like a valley that seems deep but actually sits on the edge of a much deeper chasm. The mathematics of this false vacuum state can, once again, contain a tachyonic mode. If this were true, it would mean our entire universe is in a supercooled state, similar to that water just waiting to freeze. A random quantum fluctuation somewhere in space could trigger a catastrophic process of true vacuum decay. This would begin with a tiny bubble of the true, stable vacuum forming. The laws of physics inside this bubble would be completely different from our own. This bubble would then expand outward at the speed of light, its wall a wave of total transformation. Everything it touched, planets, stars, galaxies, the very fabric of space-time and the constants of nature, would be instantly and irrevocably rewritten into a new reality governed by different physical laws. From our perspective, it would be the end of everything we know, not with a bang, but with a silent, light-speed overwrite of reality itself. In this terrifying and magnificent scenario, the tachyon-condensate is not the giver of mass, but the herald of universal rebirth, a fundamental reset button woven into the code of existence. Given the elusive and mysterious nature of dark matter, it's only natural that physicists have looked beyond conventional explanations, and tachyons, with their exotic properties, present a fascinating, if highly speculative, possibility. Could these faster-than-light particles be hiding in plain sight, masquerading as the invisible mass that holds galaxies together? The idea isn't as far-fetched as it might seem. Dark matter doesn't interact with light or ordinary matter in any way we can directly detect. Its presence is inferred solely through its gravitational pull on stars and galaxies. Tachyons, if they exist and don't interact with the electromagnetic force, would be just as invisible, forever zipping through space without leaving a conventional trace. The connection deepens when we consider gravity. Some theoretical models suggest that particles with imaginary mass, like tachyons, could exhibit negative gravitational mass. This means they would repel rather than attract ordinary matter. At first glance, this seems to directly contradict the role of dark matter, which acts as a gravitational glue. However, the universe is full of surprises. It's possible that under certain conditions or within specific field configurations, a tachyonic field could produce an overall attractive gravitational effect on cosmic scales. Alternatively, perhaps a mixture of ordinary attractive gravity and tachyonic repulsion could somehow balance out to mimic the gravitational effects we attribute to dark matter. This is frontier speculation, but it highlights how the bizarre properties of tachyons force us to reconsider even the most established cosmic puzzles. Another tantalizing link comes from the concept of tachyon-condensation. As we've discussed in quantum field theory, a tachyon signifies an unstable state that wants to condense into a stable one. What if the dark matter permeating the cosmos isn't made of discrete particles like WIMP or actions, but is rather a manifestation of a cosmic tachyonic field that has already condensed? This condensed field could be spread uniformly throughout space, invisible to our telescopes because it doesn't emit or absorb light, yet contributing to the overall mass of the universe through its energy density. Its presence would be felt only through gravity, perfectly matching the description of dark matter. In this view, dark matter isn't a collection of particles but a background sea of energy left over from a phase transition in the early universe, a frozen-in remnant of a field that once was tachyonic. The energy scales involved also offer an intriguing parallel. Dark matter is thought to have been created in the immense heat of the Big Bang, and its properties are tied to physics at incredibly high energies. Tachyons, by their very nature, are also creatures of high-energy physics, emerging from the extreme regimes described by relativity and quantum field theory. This shared domain doesn't prove a connection, but it opens a door to imagining that the solutions to both mysteries, dark matter and faster-than-light particles, might be found in the same theoretical space, a realm where our everyday intuition fails and the laws of physics operate in their most raw and fundamental form. Of course, this remains a highly speculative avenue of research, one that most mainstream physicists view with deep skepticism. The primary objection returns to causality. If tachyons are real and can interact gravitationally, even weakly, could they still transmit information and create paradoxes? If dark matter is tachyonic, does that mean the glue holding our galaxies together is fundamentally a causal? This is a major philosophical and physical hurdle. However, it's possible that a fully developed theory of quantum gravity, a theory that successfully merges general relativity with quantum mechanics, could provide a framework where these tachyonic effects are somehow censored or integrated in a way that preserves causality on macroscopic scales. Until we have that final theory, the connection between tachyons and dark matter remains one of the most captivating what-if scenarios in cosmology, a testament to the power of theoretical physics to explore the deepest and most hidden layers of reality. But beyond the immediate dangers of paradox, the very existence of tachyons would force us to confront a host of ethical dilemmas that make our current debates about artificial intelligence or genetic engineering seem almost quaint by comparison. The most immediate concern would be the utter annihilation of privacy on a cosmic scale. Imagine a surveillance technology not limited by the speed of light. A government or corporation could, in theory, position tachyon emitters and receivers throughout the solar system, creating a real-time monitoring network that could watch every event on Earth or any other planet without any delay. There would be no such thing as a secret. Every conversation, every action, every moment could be observed instantaneously from light years away, creating an ultimate panopticon where the concept of a private life becomes utterly obsolete. The power imbalance this would create is staggering, potentially leading to a form of totalitarian control that is absolute and inescapable, all enabled by particles that rewrite the rules of information itself. The ethical stakes become almost unimaginable when we consider the potential for altering events, or at least the perception of events. While the grandfather paradox presents a logical problem, what about more subtle interventions? If you could send a message to the past, even if it was just to a single person, you could fundamentally alter the course of their life with a piece of information they were never meant to have. This raises a profound question: who gets to decide what information is sent backwards? Would a global governing body be established to control access to tachyon technology, effectively deciding which moments in history are allowed to be corrected and which are not? The temptation to prevent tragedies would be overwhelming. Would it be ethical to not send a warning about a preventable disaster, knowing you had the power to stop it? Yet, every intervention, no matter how well-intentioned, could have cascading and unpredictable consequences, creating a moral burden that no single person or institution could possibly be prepared to bear. This leads us to the terrifying potential for historical revisionism and propaganda on an unprecedented scale. Control over tachyon communication wouldn't just be about sending messages, it could be about controlling the very narrative of reality. A regime could bombard the past with fabricated information, creating a false history that benefits them in the present. They could discredit movements, erase achievements, or implant ideas that never originated organically, creating a society built on a foundation of lies that are physically verifiable from the past. The very notion of objective truth could collapse if we could no longer trust that the events of history unfolded without external, temporally displaced manipulation. We would be living in a world where the past is as malleable as the future, and the responsibility to wield that power ethically is a weight that challenges the core of human morality. Ultimately, the discovery of tachyons would force humanity to undergo a rapid and radical evolution in our ethical thinking. We would have to develop entirely new philosophical frameworks to grapple with concepts of responsibility, consent, and justice across time. Does a person in the present have the right to make decisions that affect someone in the past who cannot possibly consent? What does justice look like for a crime committed using time-displaced information? Our current legal and moral systems are built on a linear cause and effect progression of time. Tachyons would shatter that foundation, requiring us to build a new understanding of ethics that operates in multiple temporal directions at once, a challenge that would demand wisdom we have not yet been forced to cultivate. While mainstream physics often treats tachyons as a problematic curiosity, their disruptive potential makes them a compelling subject for alternative theories that seek to rewrite the fundamental rules of the game. These frameworks don't just try to slot tachyons into our existing understanding, they propose entirely new architectures for reality itself, often using the tachyons' paradoxes as a starting point for a grander unification. One of the most prominent of these is the study of superluminal reference frames. In standard relativity, it's impossible to construct a reference frame that moves faster than light. The math simply breaks down. But some theorists have asked, what if we could? By developing a consistent mathematical description of such a frame, they find that the concept of causality might be preserved, but in a dramatically different way. In a superluminal frame, the roles of space and time could be swapped, and what we perceive as a violation of cause and effect might simply be the natural order of events from that perspective. This doesn't erase the paradox for us, but it suggests a larger, more complex space-time geometry where our linear experience of time is just one slice of a much richer and stranger whole. Another radical approach comes from theories that challenge the very notion of a fixed objective reality. In certain interpretations of quantum mechanics, particularly those influenced by Bayesian probability, the past is not a fixed set of events but is itself probabilistic and can be updated by future measurements. In such a worldview, a tachyon signal from the future wouldn't create a logical contradiction. It would simply force a Bayesian update of the past's probability distribution. The universe's history would remain consistent because the cause and effect are part of a single, self-consistent web of quantum correlations, not a linear chain of billiard balls. This view treats the flow of time not as a fundamental property of the universe, but as an emergent phenomenon related to how we process information, offering a potential escape from the rigid causality that tachyons seem to threaten. Perhaps the most ambitious attempts to rehabilitate tachyons come from theories that seek to unify gravity and quantum mechanics. Loop quantum gravity, a major competitor to string theory, offers a granular picture of spacetime where space and time are quantized. In this discrete structure, the continuous symmetries of special relativity might only be approximations. Some researchers speculate that in such a framework, the precise conditions that lead to causality violations in a continuous spacetime might be avoided. A tachyon propagating through this quantum foam might encounter fundamental limitations that prevent it from being used to create a true paradox, effectively having its most dangerous feature censored by the underlying graininess of reality before it can manifest on a larger scale. Other speculative models propose that tachyons are not independent particles at all, but are instead emergent phenomena, much like sound waves in a material. In these emergent spacetime theories, what we perceive as the vacuum is actually a complex condensate of more fundamental entities. A tachyon could be an excitation in this condensate that behaves superluminally relative to the background, but its ability to transmit information and create paradoxes could be limited by the same underlying physics that gives rise to it, just as a sound wave cannot carry a signal that would break the causality of the atoms it travels through. This would effectively quarantine tachyons, allowing them to exist as mathematical curiosities or even detectable phenomena, without granting them the universe-breaking power to send messages into the past, preserving a stable cosmic order even within a more exotic and malleable conception of reality. To grasp how physicists handle the mathematics of imaginary mass, we first need to revisit the cornerstone equation of motion in Einstein's special relativity. The total energy of a particle is given by a deceptively simple formula. E squared equals m squared c to the fourth plus p squared c squared, where m is the rest mass, c is the speed of light, and p is the momentum. For any ordinary particle with real, positive mass, this equation works perfectly. The term m squared c to the fourth is a positive number, ensuring that the energy required to accelerate the particle increases the closer it gets to the speed of light, approaching infinity at the barrier itself. This is the mathematical representation of the universal speed limit. The intrigue begins when we mathematically permit a particle to exceed light speed. If we plug a velocity greater than c into the equations of special relativity, the term for gamma, the Lorentz factor, becomes the square root of a negative number. This is an imaginary number. Consequently, for the energy equation to remain mathematically consistent and yield a real value for energy which we expect to be a measurable physical quantity, the mass term m itself must also become imaginary. This is how we arrive at the concept of a particle with an imaginary rest mass. It's not a random invention. It's the only way to mathematically salvage the energy equation for superluminal speeds and keep the energy value a real number that could correspond to something physically observable. The imaginary mass is the key that keeps the mathematical framework from breaking down entirely when we venture beyond light speed. Physicists then work with this imaginary mass by treating it as a perfectly valid mathematical object. They represent it as I multiplied by a real number, often denoted as I mu, where the Greek letter mu represents a positive real number. This mu acts as a kind of tachyon mass parameter, a measure of how tachyonic the particle is, even if we can't place it on a scale. When you substitute m equals I mu into the energy equation, the I squared term becomes -1, flipping the sign of the mass term. The equation transforms into E squared equals P squared C squared minus mu squared C to the fourth. This new equation is the fundamental descriptor of a tachyon's energy-momentum relationship, and it has stunning implications. This flipped equation dictates the tachyon's bizarre behavior. For a tachyon to have real energy, the term p squared c squared must be greater than mu squared c to the fourth. This means a tachyon can never be at rest. It must always have a minimum momentum to exist. More fascinatingly, if you look at how its speed relates to its energy, the math shows that as the tachyon's energy increases, its speed actually decreases, approaching the speed of light from above. Conversely, as the tachyon loses energy, its speed increases towards infinity. This is the precise mathematical origin of that counterintuitive car in reverse behavior, all derived directly from plugging an imaginary mass into Einstein's own equations. The mathematics isn't just describing a weird particle, it's painting a picture of a complete inversion of the kinematic rules we hold dear. This mathematical treatment isn't just an abstract exercise. It allows physicists to formally incorporate tachyons into the broader framework of quantum field theory, constructing models known as tachyon fields. In this context, a field with an imaginary mass parameter is said to have a negative mass squared. This condition is the mathematical signature of an instability. The equations describe a system that is not at its lowest energy state. It's perched precariously and wants to roll down to a stable configuration. This process is called tachyon-condensation. So, while the math of imaginary mass allows us to model faster than light particles, its more profound and practical application in modern physics is as a diagnostic tool. It's a red flag in the equations that signals a phase transition is imminent, a mathematical harbinger of a system on the verge of transforming into something new and stable, much like the Higgs field did at the beginning of our universe. This journey through the paradoxes and possibilities of tachyons now leads us to one of the most profound mysteries in all of cosmology, the accelerating expansion of the universe. For decades, we've known that not only is the cosmos expanding, but this expansion is speeding up, driven by an unknown force dubbed dark energy. The leading explanation points to a cosmological constant, a uniform energy density inherent to the vacuum of space itself. But this model has its own deep puzzles, leading some theorists to ask a radical question. Could the same exotic physics that gives us tachyons also hold the key to understanding dark energy? The connection emerges from the unique behavior of tachyonic fields. Remember, in quantum field theory, a field with a negative mass squared is tachyonic, indicating an instability. But what if such a field didn't rapidly condense and settle down like the Higgs field did? What if it persisted, evolving over the entire history of the universe? This is the premise of theories involving tachyonic dark energy. In these models, the cosmos is permeated by a dynamic scalar field, a field with a value that can change over time and space, whose potential energy is shaped by that characteristic unstable, hill-like form. The field is constantly rolling toward stability, but its evolution is slow and gradual, stretched across billions of years. This slow roll has a direct and dramatic consequence. It can generate a sustained negative pressure throughout the fabric of spacetime. In the equations of general relativity, pressure contributes to gravity. Ordinary positive pressure, like the intense pressure at the core of a star, adds to the attractive force of gravity. But negative pressure does the opposite. It acts as a form of repulsive gravity, a kind of anti-gravitational force that pushes spacetime apart. This is precisely the effect needed to explain the observed acceleration of the universe's expansion. A tachyonic field, by its very nature of being off-kilter and seeking a lower energy state, could naturally produce this pervasive negative pressure, acting as an engine for cosmic acceleration. The appeal of this idea lies in its dynamic nature. The standard cosmological constant model is static. The energy density of the vacuum remains unchanged as the universe expands. A tachyonic field, however, offers an evolving form of dark energy. Its energy density could change over time, potentially offering an explanation for why the acceleration rate of the universe appears to have changed throughout cosmic history. This could solve several fine-tuning problems associated with the cosmological constant, providing a more natural narrative for why we observe the specific amount of dark energy we do today. It transforms dark energy from a mysterious fixed number in the universe's equations into a physical entity with a history and an evolution, a field with behavior we can potentially model and predict. Yet, this compelling idea is not without its own significant challenges. The same instability that makes a tachyonic field a candidate for dark energy also makes it notoriously difficult to control within a theoretical model. Such a field can be prone to developing uncontrollable inhomogeneities, where the energy density clumps in some regions and voids in others, which would conflict with the overwhelming observational evidence that dark energy is perfectly smooth and uniform across the vast reaches of space. Furthermore, the field's energy density must decay at an exquisitely precise rate to match the observed acceleration, requiring a level of fine-tuning that some physicists argue is just as mysterious as the cosmological constant it seeks to replace. The exploration of tachyonic dark energy represents a fascinating convergence of the very large and the very small, of quantum field theory and general relativity. It demonstrates how a concept born from the mathematics of faster-than-light particles can find a potential application in explaining the grandest-scale behavior of the entire cosmos. Whether this particular idea ultimately proves correct is less important than the path it illuminates. It shows that our universe's greatest mysteries, from the impossibility of superluminal travel to the force ripping galaxies apart, might not be separate puzzles at all, but different facets of a single, deeper truth about the unstable, dynamic, and utterly surprising vacuum in which we live. Looking ahead, the pursuit of tachyons is no longer just a search for a particle. It's a multifaceted exploration pushing at the very frontiers of theoretical physics, where the most profound mysteries of the universe converge. One of the most active and exciting frontiers is the quest to unite tachyon theory with a complete theory of quantum gravity. The core problem is that our current models are piecemeal. General relativity beautifully describes the cosmos on large scales, while quantum mechanics governs the tiny subatomic world, but the two theories are fundamentally incompatible. Tachyons sit directly in the crossfire of this conflict because their potential to violate causality is a gravitational concern. It warps spacetime itself, while their hypothetical existence is a quantum phenomenon. Researchers are now asking if a full theory of quantum gravity, perhaps through loop quantum gravity or causal set theory, might naturally contain mechanisms that censor or resolve the paradoxical aspects of tachyons. These frameworks propose that spacetime might not be smooth and continuous as Einstein described, but instead granular or discrete at the smallest possible scale, a structure often called spacetime foam. The idea is that a tachyon trying to create a causality-violating loop might simply not be able to navigate this foamy quantum structure in a coherent way. Its path could be disrupted or randomized at the Planck scale, effectively preventing any meaningful information from being sent backwards in time, and thus protecting the causal order of the universe we observe. This wouldn't mean tachyons can't exist. It might mean their most dangerous property is neutered by the fundamental graininess of reality, turning them from universe breakers into potentially detectable cosmic curiosities. Simultaneously, string theory continues to be a rich playground for tachyon physics, but the focus has dramatically shifted. The discovery of the Higgs boson was a monumental confirmation of the Higgs mechanism, which is mathematically analogous to tachyon-condensation. This success has energized string theorists to look for other, similar instabilities within the vast landscape of possible universes predicted by string theory. The central question is no longer, can we detect a tachyon, but rather, what does the presence of a tachyon in the spectrum of a string theory vacuum tell us about that vacuum's stability and its ultimate fate? Researchers are meticulously mapping out these unstable states, trying to understand the pathways of decay from one vacuum to another. This work is incredibly complex as it involves higher dimensional objects called D-branes, whose decay is described by a special branch of string theory known as string field theory. The ultimate goal is to use the mathematics of tachyon-condensation to understand not just the end of a single D-brane, but perhaps the birth and death of entire universes within a multiverse. Could our own universe be the product of a previous vacuum's tachyonic instability? And if so, are we now sitting in a stable valley, or are we merely in a temporarily metastable state awaiting our own triggering event? These are the grand, cosmic-scale questions that tachyon research now grapples with. Perhaps the most tantalizing direction for future research lies in the search for observable consequences. How could something so theoretical ever be tested? Astronomers and cosmologists are rising to the challenge, designing ingenious ways to look for the faint imprint of tachyonic phenomena on the cosmos itself. One promising avenue involves the study of the cosmic microwave background radiation, the ancient afterglow of the Big Bang. The patterns in this radiation are a fossil record of the universe's earliest moments. Some models suggest that if a tachyonic field played a role in the universe's early inflationary phase, the period of rapid expansion just after the Big Bang, it could have left a distinctive signature in the polarization patterns of this background radiation. Powerful next-generation telescopes like the Simon Observatory and the Lightbird satellite mission will be scanning the sky with unprecedented sensitivity, and physicists will be poring over their data, not just for signs of primordial gravitational waves, but for any statistical anomaly that might hint at exotic physics like tachyonic inflation. Another approach looks to the high-energy frontier of the universe. When the most powerful cosmic events occur, like the mergers of black holes or neutron stars, they ripple the fabric of space-time, sending out gravitational waves that we can now detect with observatories like LIGO and Virgo. The properties of these waves are exquisitely sensitive to the laws of physics that govern their creation. Theorists are now modeling whether the presence of tachyonic fields could subtly alter the way these gravitational waves propagate or how they are generated. It's a long shot, but by comparing the predictions of these exotic models against the vast catalog of real gravitational wave events, scientists might one day find a discrepancy that points toward new physics. Furthermore, the immense energies released in these collisions could, in theory, be a natural production site for tachyons if they do exist. While we couldn't detect the tachyon itself, its creation might steal a minuscule amount of energy from the collision, leaving a telltale signature in the gravitational wave signal that it's slightly weaker than our standard models predict. We are moving into an era where we are no longer just looking for the particles themselves, but for their subtle, ghostly shadows cast upon the only signals that can travel from the most extreme environments in the cosmos. The hunt has evolved from a direct search to a forensic investigation of the universe's most violent events, seeking the faintest clues of a reality that operates by a different set of rules. Beyond the equations and experimental searches, the true power of the tachyon concept lies in its profound philosophical weight, forcing us to confront the very nature of reality and the limits of human knowledge. For centuries, our understanding of the universe was built on a foundation of absolute time and space, a stage upon which events unfolded in a strict, linear sequence. Einstein's relativity revolutionized this by weaving space and time into a single, flexible fabric called space-time, but it still preserved one sacred rule: the unbreakable chain of cause and effect enforced by the cosmic speed limit of light. Tachyons represent the first credible mathematical challenge to this final pillar, suggesting that this causal structure might not be a fundamental law of the universe, but merely a local byproduct of the slow-moving, mass-bound reality we happen to inhabit. This forces a radical shift in perspective from a universe governed by fixed rules to one of relative laws. If tachyons exist, the flow of time and the very sequence of events would not be absolute truths, but would depend entirely on the observer's state of motion. What appears as a clear cause and effect to one observer could be a baffling effect preceding its cause to another. This doesn't just add a new particle to the menagerie of physics. It implies that the logical consistency of reality itself, the principle that allows us to do science, to predict outcomes, and to believe in a shared, objective past, might be a fragile illusion, a stable island in a much wilder and more paradoxical cosmic ocean. It asks whether the laws we've discovered are truly universal commandments or simply the familiar, comfortable rules of our own limited neighborhood. Ultimately, the tachyon is a testament to the power of scientific imagination. It demonstrates that even our most cherished and successful theories are not the final word, but are instead invitations to ask deeper, more disruptive questions. The value of the tachyon may never be in its physical detection, but in its role as a permanent provocateur, a reminder that the universe is under no obligation to conform to our human intuition about how things should work. It keeps the door to wonder wide open, ensuring that physics remains not just a process of discovery, but an endless adventure into the possible. And so our journey through the enigmatic world of tachyons brings us to a profound realization. This isn't merely a story about a hypothetical particle. It's a powerful testament to the human spirit's relentless drive to question, to explore, and to push beyond the boundaries of the known. From a curious mathematical solution in Einstein's equations to a named concept that challenges our deepest understanding of causality, the tachyon represents an idea so radical that it forces us to re-examine the very fabric of reality, time, and our place in the cosmos. It showcases the beautiful, often audacious process of science, not as a collection of settled facts, but as a dynamic conversation with the universe, filled with thrilling, what-if scenarios that stretch our imagination to its absolute limits. Whether tachyons truly exist as physical entities may remain one of physics' greatest open questions, but their incredible value lies in the doors they have opened. They have compelled us to sharpen our theories, to confront unsettling paradoxes, and to dream of technologies that border on magic, from instantaneous communication across interstellar distances to computers that process information outside the flow of time. They have even provided a surprising lens through which to view cosmic mysteries like dark energy and the stability of the vacuum itself. The ghost of the tachyon, whether real or not, has already irrevocably expanded our perspective, reminding us that the universe is likely far stranger, more complex, and more magnificent than we have yet dared to imagine. This conversation doesn't end here, it's just beginning. Now we want to hear from you. Do you think nature could truly permit such extraordinary phenomena, hidden in plain sight, waiting for a future generation to discover? Or are tachyons a fascinating mathematical mirage, a door the universe has firmly locked to protect the logical order we rely on? Share your thoughts, your wildest theories, and your questions in the comments below. Let's keep this incredible exploration of the cosmos going. And if you enjoyed this journey to the edge of physics, be sure to like this video and subscribe for more deep dives into the ideas that define our reality. Until next time, keep looking up and keep wondering.